All right, so tonight we're going to look at polar coordinates. So polar coordinates have two distinct pieces of information. It is going to be the radius and the theta. So when you look at a polar coordinate, let's see if I can switch it here. So this is what a polar coordinate typically ends up looking like. You'll have the circles. So if you've ever seen a circle graph, that's what the polar coordinates are. And you notice that we don't have the typical x and y axis in this. You have your radius axis, which is actually both axes here. That's the same thing. And then you have your basically like your unit circle going around. Those are your thetas. So when you're graphing a point in polar, you're going to tell me which the angle is and then how much the radius is, and that's how far you're going to go out from the center. So that's what we're going to be looking at tonight. So here's a quick little example of it. We have our point is r comma theta, so that's the radius and the theta. And the theta is how far away from the polar axis we are, so how far we are away from that, the x-axis or the polar axis, the horizontal line. And the radius is how far I'm going out from the origin or the center of the graph. We will look at a way to be able to convert the polar coordinate to a Cartesian point and back from a Cartesian point to a polar coordinate as well. A couple things to notice when we're looking at the thetas is that we can have multiple ones that equal the exact same thing. So one example would be if I had the radius and theta, that's one point. But if I had the negative radius, it's not the things that are going to change is you actually graph it the same way and then you just go the opposite direction with the radius. So, but that's equal to the exact same thing as saying theta plus pi, because pi would be 1/2 of the rotation around the circle. So it's 180 degrees. So the positive one would be this way, and the negative one is just in the opposite direction. So here's a couple examples of different points and what they look like. And we're going to actually, I'm going to show you them actually drawn out because I think it's a little bit easier when you actually see them done out. So here's the first graph. So our radius in this case was 1. And my theta was 5 pi over 4. So you can see that first point that 1, 5 pi over 4 is right there. So a radius out is 1, and then we rotate around to the 5 pi over 4, which is in the third quadrant. The next one was 2 and 3 pi. Now, when we're looking at this one of the things you're going to notice is that one full rotation around the circle is 2 pi. So to graph 3 pi, we actually are going past that, and we do one more pi. So that would be a radius of 3 and a theta of 3 pi. Notice that that is actually the exact same answer as if the radius was 3 and the theta was pi. So we can actually, that's what we're saying, we have multiple rotation or multiple answers would give you the same thing because the unit circle is only 2 pi. So we actually have multiple vertices or multiple polar coordinates that are the exact same position. The next one is 2 and negative 2 pi over 3. So when we have a negative theta, you're going clockwise instead of counterclockwise. So that's the negative 2 pi over 3. And another way, if you wanted to look at that in the positive version, it would be the radius. And then if we went the other direction for it, it would be I can't think right now. 4 pi over 3. Sorry. Simple subtraction eludes me this morning or this afternoon. So it'd be 4 pi over 3 in the other direction. Now the last one is negative 3 is my radius and 3 pi over 4. So now we're looking at this one. we graph our original function. So that's my original theta. And then when I want negative, the negative goes the other direction. So I graph that one, and then I go this basically a vertical line for, or not necessarily a vertical line, but a continuing that line in the other direction. So those would be how we graph our polar coordinates. Any questions on those? Okay. This is what we were talking about, where the same points are going to be two n pi's, so you can actually go back and forth directions of them. And the negative ones would be the exact same as the 2n plus 1. So it's the you're adding just pi to it, basically. When we're looking at what's their connection back to the Cartesian coordinates, we actually look back at them as just like we're doing with the Pythagorean theorem. So I have my theta there. My radius is the hypotenuse of my triangle. And then we have the x and the y coordinates. When we're trying to find those points, we have to do our calculations from it. So cosine of theta is x over the r, and sine theta is y over r. Those are just your typical same things with your trig functions. So if we solve those for x and y, x will be r cosine theta and y will be r sine theta. So this allows us to convert a polar coordinate to a Cartesian coordinate. So if I have the r and the theta, I can figure out my x and my y. Also the Pythagorean theorem also does work. R squared equals x squared plus y squared. So tangent of theta equals y over x. This will allow us to take a polar or a Cartesian coordinate x and y and convert it back into a polar coordinate. So this will help if I have the x and the y, the r squared, that'll help me find my radius. And the tangent of theta with the y and the x will help me find my theta. Everybody got those two equations written down? All right, let's use them. So example 2, when we're looking at, we're going to convert the point 2 pi over 3 from a polar to Cartesian coordinates. So my r is 2, and my theta is pi over 3. So we're just going to plug those into the equation, r cosine theta and r sine theta. So r is 2, that's simple. Cosine of pi over 3 is 1/2. And sine of pi over 3 is square root of 3 over 2. If you don't remember those, that's the unit circle. So if you think back to when you did pre-calculus, they gave you that unit circle, or you had to calculate it out. That's what's going to be useful when you're trying to convert back and forth. So just find a quick unit circle online. There's lots of them. That'll give you those basic functions to be able to break them down. So x is 2 times 1/2, which is 1, and y is 2 times square root of 2 over 2, which is just the square root of 3. So this polar coordinate is at point 1 square root of 3 on the Cartesian plane. Any questions with that before we go the other direction? Okay. Next one we're looking at, we're going to take the Cartesian coordinates and switch it back to polar. So in this one, we have to use the r squared equals x squared plus y squared. So we're going to plug in the 1 and the negative 1. So that comes out to be the square root of 2. And then we do tangent of theta is y over x. So we have tangent of theta is negative 1. So when we're looking for the theta and you're getting the answer, so tangent of theta equals negative 1, we want to figure out which theta we're going to use for that. Now, most of your trig functions are going to have 2 thetas that work for each of your values. So for tangent, you're looking at the first and the fourth quadrant. So in this case, this one would be in the fourth quadrant, and it's going to be negative pi over 4. So you can use the square root of 2 equals negative pi over 4, or you can change it so it's a positive theta by adding 2 pi to it, and you get the 7 pi over 4. So either one of those two answers would work and be acceptable for converting it back over. Any questions with converting them back and forth or doing the simple graphs of them? Now we're going to start looking at what an equation would be. All right. So in polar curves, if we graph the equation r equals 2, for example, actually I'm going to make this r equals 5 so it's going to be a little bit bigger. So if I was to graph r equals 5, I have a circle. If I was to graph r equals 9, I have a circle with a radius of 9. So if you think back to when we're doing Cartesian coordinates, when you have x equals and y equals, you get straight lines. Well, when we're looking at polar coordinates, when you have just the r, you're actually going to get a circle because that radius, the theta is everything in this situation. So that is the same thing as having a horizontal or vertical line in our Cartesian plane. So your radius is 9, your radius is 5, you're going to get a circle with that much of a radius. If we had theta equals 1, let me graph that one. That's not going to give me theta equals 1. So when you're graphing theta, if theta equals, let's see if let me actually do pi. Nope. Theta will actually give you the straight line. So if you have theta in all the radiuses, so you're going to have that angle. So if it was theta equals pi, it would be a horizontal line from the origin out all the way out, and it would just keep going because the r doesn't matter. The r is for any value. So that's how what a graph of theta. Let's see if I have one in here so I can show you. Nope. So yeah, when you're graphing theta, it's just going to be a straight line. Next, let's look at some curves. So when you're graphing them, if you did r equals, let's say 2 cosine theta. So here's r 2 cosine theta. And if we're looking at this, notice how the values are going to change on this one. So if we look, they don't give me this graph either. So hold on one second. Let me get you this graph. I want to show you the table of it. So this is what the table would look like. So if theta is 0, my radius is 2. If theta is pi over 6, my radius is square root of 3. So notice that my radius is not fixed in this function. So as my thetas change, my radius changes. So we're not going to get that perfect circle type graph. It kind of looks like a circle when we're looking at it, but when you zoom in a little bit, you'll notice that it's elongated. So it doesn't actually work out to be exactly a circle. And that's because as my theta changes, my radius changes. It's not always going to be the exact same radius. Does that make sense when you're looking at the graph, the table like that?
I think so. It'll just take time to process.
Yeah, it's one of those things like you actually have to try it and see how it works. Let's actually do one real quick. So you can actually see one done out. Let's graph. Let's graph 3 sine theta. So when you're looking at these, you want to actually, so when you're picking values, so your theta is the value that you're picking, and your r is what you're going to find out. So if we did sine of, if my theta is 0, sine of 0 is 0. So my radius is going to be 0. If I did sine of pi over 2, sine of pi over 2 is square root of 2 over 2. So it's 3 times the square root of 2 over 2. Oh, sorry, that's pi over 4, not pi over 2. If we did pi over 2, sine of pi over 2 is 0. So this now goes back to 0. If we did 3 pi over 4, that's going to be negative square root of 2 over 2. So this will be negative 3 square root of 2 over 2. And if we did pi, now when you're going down to pi, sine's going to be negative 1, so that's going to be negative 3. So now let's look at that on the graph. Oh, I messed that one up. I did mess that up. So pi over 2 of sine is actually is 1, so that's 3. Pi is 0, so that goes back down to 0. So as you can look at this graph here, so I mixed those up. So we start off at 0, and then when we get up to pi over 4, so pi over 4 is right here, that's where you have that 3 square root of 2 over 2. So that's a little bit bigger than 2 on my radius. When you get to pi over 2, your radius is 3. And then we get back down to here, your radius is negative. So I'm going the opposite direction now. And then when I get back to 0, it's back down, or we get back to pi, my radius is 0 again. So you have that circle. Now, if I was to extend this out instead of doing 0 to pi over, or just pi, if I did 0 to 2 pi, it's the same thing. We don't actually change it because sine repeats itself on the other end. So the values are going to be the same as you keep going around. All right, let's look at one that's going to be a little crazier. It's called the cardioid. So if we were to graph the curve 1 plus sine theta, so all the ones we did so far have been multiplication. So If we look at 1 plus sine theta, that's just the sine curve shifted up by 1. So these are my theta values. And this curve tells me my radius. So notice how the radius starts off at 1, goes up to 2, back down to 1, down to 0, and then back up to 1. So that's what my radius does as I go through my curve. If we look at just the first part of it, this is what the graph would look like. So the first 0 is theta, I'm at 1. And when as I get up to theta is pi over 2, I get to 2. So my radius is getting bigger and bigger as I go up. So this 2. Does that make sense?
Yeah.
All right. So that was this part right here. So now if we look at the next part from 0 to, or from pi over 2 to pi, it kind of repeats itself, but it's getting smaller. So when I look at the next part of that graph, you can start seeing it repeats itself, but now it's getting back down to that 1 value. So now that we've looked at the first part of the graph, what do you think is going to happen with the second part of this graph?
It's gonna do the exact opposite.
What do you mean by the exact opposite?
Like it's gonna start out getting smaller and then get bigger the other way.
So it's going to get smaller, but is it going to get smaller the same way that would be up here, or is it actually is it already starting smaller?
Well, yeah, it's starting off where the other one ended, right?
Yeah, so it's going to do the same basic thing, but as you can see here, it's a very small curve because it's all those values are actually less than 1 at this point. So my radius at this point was 1, and it's going to 0. So where the one we just looked at started off at 1 and went to 2, so that was a rather large radius. So this one's starting off at 1 and going down to 0. So it's kind of doing that little point back to the 0 point. And then the other one is doing the exact opposite. It's starting off at 0 and going back off to 1. So we get that cool little graph, which is known as a cardioid, because it's kind of shaped like a heart. I suppose you could say it looks like other things, but we're going to go with it looks like a heart because that's nicer than the other things. So that's a typical curve. So if you ever hear the word cardioid, that's what it actually means. That's what it looks like in the mathematics version of it. All right. Let's look at another one. Let's look at this one. All right, so I told you I could do some cool graphs with polar coordinates. So this is also just another polar curve. But notice how this one has the leaves. So if we were to look at this graph in terms of just like the x and the y, so if we looked at y equals cosine 2 theta. So if we were to look at this graph right here, so this is just y equals 2 cosine theta. No, let me do 3. You can see how it starts off at 1, goes to 0, comes back up, and it keeps repeating itself over and over again. So when we're looking at, so now to 2 pi, I'd be going all the way out to right here. Actually, 2 pi, it's up there, sorry. So I was going out to 2 pi, it's there. So you notice how we got this one curve, then we've got the second curve. So we've got like 2 curves here. But the values going down are the exact same as the values going up. They're just the reverse of them. And that's what happens when you look at this curve right here. That's what you get. So if we just look at the first one, let's look at just from pi over 2. So pi over 4. So that's just that first one. That's just a pi over 4. So that's from this point right here to that. So we're looking from that point to that point, and that's what that curve is going to do. So if we're just looking at that first part right there, that's what that green line is doing on the curve. When we add in the pi over 2, so we're going to look at the second part of it. So if we look at pi over 4, to pi over 2, that's this part down here. So because we're going all my radiuses down here, all those radiuses are going to be negatives. So we're going to graph the curve, and then we're going in the opposite direction. So since we're graphing the pi, the theta is over here. Since it's negative, it's going to reverse down into the third quadrant. Does that make sense?
Yeah.
All right. So now if we look at the next part of this, if we look at pi over 2 to 3 pi over, or yeah, 3 pi over 4. Now this one, so we're looking at the values from here to here. So now these theta values are over in the second quadrant, but my radius is still negative. So since it's the thetas are over in the second quadrant and I reverse down, that's why my curve is in that fourth quadrant down there. And then if we look at the last curve, the last part of the, like the first set of them. So if I go from 3 pi over 4, this pi. Now this one, my radiuses were positive, and we're in the second quadrant, so it stays in that second quadrant. So if I look at one whole rotation, that right there is one curve from 0 to pi. Now, if we were to finish it off by going to 2 pi, that's when I fill in. So if I looked at actually pi to 2 pi, I get the second part of the graph. And that's from this part over here to that part. So the reason it switches, so instead of being on the bottom like the first one was, is because my thetas now that I'm working with are down in the third quadrant and the fourth quadrant. So that's why it basically takes what I figured out for the first part of it and flips the entire thing over. And that's how I get the nice little fourth leaf flower. For those of you that are playing around with your graphs, if you want more leaves, all you have to do is change the number by theta. So any odd one will give you exactly that number of leaves. Any even one will give you double the number of leaves. So if you do 4 theta, you're going to get 8 leaves. If you do 5 theta, you'll get 5. 6, you'll get 12. 7, you'll get 7. So you can play around with that. And the number in front makes it bigger or smaller. So if you make it 0.5, it makes it really small. 9 makes it really big. So, and that's just a simple, just cosine function. So you can actually play around with that a little bit if you want to, in your parametric and polar equations or graphs you're doing. All right. We kind of talked about this a little bit, the symmetry, where you have the radius on one side, the negative one on the other side. Those are symmetric. If it's the thetas change and you're in the exact same point, it's reflexive across or symmetric across the polar axis, or symmetric across the origin. So you can actually see how the symmetry will help you find some of those points. You also can have symmetry across the vertical line, where it's the same as pi minus the theta. So it's the same thing as theta and then theta minus pi, or pi minus theta. We'll give you the two things on the other sides. All right, any questions with graphing them before we go into the trig stuff? Okay. So when we're looking at trig for the polar curves, we're going to do the exact same thing that we were doing with the parametric curves. We're going to look for tangents, we're going to look for arc lengths, and we're going to look for areas. So those are the things that we're going to be looking for. We're not going to rotate it, so we're not going to have the surface area this time, which will be a little nice, but we are going to do the other three. So finding tangents, you're looking for your derivative. So your derivative function for this is a little more complicated than the parametric equations, where you just had to find the derivative of each piece. In this one, your dy over dx, or is dy d theta over dx d theta. So you actually have to find the derivative of that other part. So your function actually is dr d theta times sine theta plus r cosine theta. And notice the dr d theta is the same because we only have one function on the top and the bottom. But the other part changes. So you have sine theta plus r cosine theta on the top and cosine theta minus r sine theta on the bottom. That's how you get your the dy and the dx. And for basically all that's doing is it was taking the derivative of r cosine theta and r sine theta. And when you have the multiplication, you have to do the product rule. And that's the derivative of the first times the second, and the derivative of the second times the first. So derivative of r is your dr d theta, and then it's just sine, and then the derivative of sine is cosine. So that's where these are coming from. So when we're doing our tangent functions, we need to use that entire equation and do it out. So it makes it a little more complicated to work with. All right. So let's actually use, so the other piece that we're looking at, when we're looking for finding horizontal or vertical tangents, horizontal is where the top is 0, vertical is where the bottom is 0. And you do have to look at the cases where they're both 0. So if they're both 0, then if the bottom is 0, it makes the top 0, you're not counting that one. Same thing on the top. So if they're both 0, that point's not going to be a vertical or horizontal tangent. So you can cross off those values where they appear in both of them. All right, so let's look at our cardioid again. So if we looked back at my cardioid, let's actually regraph this one. So we have r equals 1 plus sine theta. So here's my cardioid. So if we want to find our tangent, so the first one we're going to look for is we're going to look for the tangent at pi over 3. So we want to find our tangent when theta is pi over 3. And my r is 1 plus sine theta. All right, so that's what we're looking for. So when we're looking for this, we're going to use the tangent function for. We're going to use the derivative formula. So I have, so it's dr over d theta, and then it's sine theta minus or plus r cosine theta, and dr d theta cosine theta minus r sine theta. So the first thing I have to figure out is dr d theta. So my derivative of this function, so dr over d theta, is just cosine of theta. So we have that. Now we're going to plug it into this function. So we have that part, and we have that part. So my dr d theta is cosine theta. So that's cosine theta. And then I have sine theta plus, and now I have r. R is my original function, so it's 1 plus sine theta. And then cosine theta over cosine theta cosine theta minus r. So 1 plus sine theta sine theta. So one of the things that's really quick to forget is to replace that r. And that's why I color coded it, to make sure you don't forget to replace the r. So when you're doing it, once you have the problem done and all the stuff there should be no more r's or anything else. It should only be thetas. Now let's simplify this up a little bit and clean it up so we can actually do this out instead of having it be as messy as it is. So I can pull out on the top cosine theta, and I'm left with, so I have sine theta plus 1 plus sine theta. So I have 1 plus 2 sine theta at the top. On the bottom, we're going to clean this up a little bit before I put it over there. I have cosine squared theta minus sine theta plus sine squared theta. So, hold on a second, I'm missing something. Oh, that's a minus. That's what I was missing. I forgot to distribute the minus sign. All right, so hold on a second. I'm just trying to figure out how they actually did this. They lost a cosine here somewhere. Oh, I see. Okay, so to keep them all as cosines, they changed this to 1 minus sine squared theta. The cosine goes to that. So then this whole bottom part goes to 1 minus sine theta minus 2 sine squared theta. which you can factor to 1 plus sine theta, and then 1 minus 2 sine theta. So my derivative for this, so does that part make sense? And the entire reason for them to do this is it makes it easier to do the calculations a little later on. You could have left it with the cosine squareds and everything else in it. It wouldn't have actually mattered. It just makes your calculations a little harder later. Any questions with how I found the derivative before we go on and actually use it?
So at the very beginning, how did you get the cosine?
You did the derivative of 1 plus sine theta,
Oh, okay.
because that's what the drd theta is. It's a derivative of whatever r is. Any other questions with that one? All right. I will switch it over in a second. So So we have that, and we're looking for the tangent at theta equals pi over 3. So what we're going to do is we're basically going to plug in pi over 3 to all the thetas. Oh, I missed my theta right there. So cosine of pi over 3 is 1/2. 1 plus sine of pi over 3 is square root of 3 over 2 times 2, so that would be just square root of 3 over 1 plus square root of 3 over 2, and then 1 minus square root of 3. So simplify this down. And we end up getting 1 plus square root of 3 over negative 1 minus square root of 3, which ends up coming out to be negative 1. So my slope at that is negative 1 at that point. Once we have our point, if we wanted to find my equation for it, we would have to get the point at where theta is pi over 3 and the radius, and then plug it into the y equals mx plus b equation to get the actual equation for it. But this problem was just looking for the slope of it. Any questions with that?
No.
Okay. So the next part we want to do is we want to figure out where my horizontal and my vertical tangents are. And that was actually the reason why we broke it down as much as we did originally, because I have to be able to figure out zeros. And when I have it as factored out, it allows me to find out the zeros a little bit easier. So for vertical, I'm setting the top, so cosine theta, and then 1 plus 2 sine theta equal to 0. So which values are going to give me 0 for cosine of my unit circle?
0 and negative 1. Yeah.
Okay, hold on. We're looking for the thetas. So if theta was 0, cosine is 1. So when you're looking at the thetas, you're basically looking at that unit circle values. So we're looking at the hold on a second. Let me actually find a unit circle real quick. I'll show you. So it actually would behoove everybody if you get one of these. And I really like this one. So we're looking for where the cosine is going to be 0. And remember, cosine is your x values. So cosine is 0 at pi over 2. And cosine is 0 at 3 pi over 2. So those are going to be the zeros for your cosine. So pi over 2 and 3 pi over 2. And that's the cosine of theta 1. Does that make sense?
Yeah.
All right. Now, for the 1 plus 2 sine theta equals 0, I have to solve this. So this is going to end up being sine theta equals -1/2. So if we go back to my unit circle, we're looking for the values of sine that are going to give me -1/2. And remember, we're looking for the y values. So -1/2 is at 7 pi over 6. And 11 pi over 6. So those are the two values that are going to give me 0 for that one. Now in horizontal, we're looking at the bottom part equals 0. So if we're looking at the 1 plus sine theta, that's where sine theta equals -1. So again, we go back to the unit circle. We're looking for the y values equaling -1. And the only one that works for that is 3 pi over 2. And then I do the 1 minus 2 sine theta equals 0. So I'm looking for sine of theta equals +1/2 for this one. So I go back to the unit circle. So we're looking for +1/2. So that would be pi over 6. And 5 pi over 6. All right, does that make sense?
Yeah.
Yeah.
All right, now we're not done because remember we have situations where we can't have 0 on the top and 0 on the bottom. So when we're looking at the rest of these values, the only one that appears in both of them is the 3 pi over 2. So the pi over 2 works for the vertical, 7 pi over 6, and 11 pi over 6. Those all work for the vertical. For horizontal, we have pi over 6 and 5 pi over 6. So the 3 pi over 2, since we have 0 over 0, is not a vertical tangent for this one. So we don't have to worry about the 3 pi over 2 one. And if we look at the cardioid, we have our vertical tangents right over here. So that's the pi over 2. Oh, sorry. It's backwards. I had them completely backwards. I wrote vertical and horizontal backwards. So horizontal was at the pi over 2. I reversed them. I'm really off today. So horizontal's at pi over 2, and 7 pi over 6, and 11 pi over 6. And then my vertical tangents are at pi over 6 and 5 pi over 6. So on the two sides. There and there. And notice how at 3 pi over 2, it actually comes to that point. So that's not a vertical or a horizontal tangent. Questions with that? So horizontal and vertical. All right, so that's how we find the tangents of the graph. So as you can tell, it's a little more complicated than the parametric equation to find it because there's other stuff there because we're dealing with the trig functions. So. All right, next up. Areas and arc lengths. So when we're looking for area of a circle, it's pi r squared. Now, when we're looking at it in terms of with radians or with the theta in there, it's pi r squared, but that theta is going to go all the way up to 2 pi. So that's where the 1/2 comes in to make it, so it's basically the circle would be pi r squared. Theta allows us to do any of the central angles. So in this case, that would come up with the area of the sector. The problem is if my radius is changing, it's not just a simple little formula there. So my radius is going to actually be a function there. And then to find out my area under it, we actually have to do the integral of that because it's going to change as the r changes. So all the hopey tall stuff, that is the formula for it. So notice it's very similar to what we just did. So it's the 1/2 the radius squared, and then it's times d theta. So it's the derivative of, it's going to be in terms of theta at that point. And the 1/2 will just come out in front. The a to the b should be in terms of thetas because those are going to be the angles that you're starting at and stopping at. The one thing when you're looking at the a and the b is working with symmetry on it, because if you look for the whole thing, a lot of times it'll cancel each other out and you'll end up getting 0 for the area because you're looking at the stuff above and below. So you do want to actually make sure you're paying attention to that. And that's the first example we're going to look at actually has that problem in it. So, all right. So if we're going to look for this one, so we're going to look at one of those 4-leaf rose pieces. So when we did this original problem, if you noticed when I did it, let's actually put this back in here. Cosine. All right. So now, if we look at 0 to 2 pi, I've got the whole curve there. But if we only want to find one of the leaves, remember, I can't do 0 to pi over 2 because that doesn't make a leaf. But if I did negative pi over 4 to pi over 4, I get one of the leaves. What do you notice about that one leaf, though? that could cause us problems if we were looking for the area of it. The top part here is the same as the bottom part here. So if I looked for the area from negative pi over 4 to pi over 4, it's going to be 0 because they'll cancel each other out. So when I'm looking at a thing like this, we want to look at it in terms of symmetry. So when we do this problem out, instead of doing negative pi over 4 to pi over 4, I'm just going to do 0 to pi over 4. And then I just have to multiply this function by 2 because I have 2 of them. Does that part make sense?
Yeah, it's like what we did for like the first chapter we did.
Yeah, exactly. When you were looking for it. So instead of doing the whole thing, we just do the piece of it. And basically there's no 2 in front of it because we have to pull out the half, and the half and the 2 cancel out. So that's why there's nothing in front of it. We don't have the 2 there. So we're looking for so remember R was cosine theta or 2 theta. So I'm looking for the integral of cosine squared 2 theta. We can't do cosine squared. So I have to use the half angle formulas. So I have 1/2 times 1 plus cosine 4 theta. And it's 4 because there was already a 2 there. So it doubled it. So I can pull back out the half, and then I do the integral of 1, which is theta, and the integral of cosine 4 theta, which is 1/4 sine 4 theta. Now in this one, if I'm plugging in 0 to pi over 4, the 0 is going to cancel out that part, and the 0 is going to cancel out that part because sine is 0, 0, so that we don't have to worry about the 0 one. The pi over 4 is there. Sine of 4 pi over 4. So 4 times pi over 4 is sine of pi. Sine of pi is also 0. So all I have left is 1/2 times pi over 4, which is pi over 8. So that is the area of that one leaf is pi over 8.
Did you already would it need to be multiplied by 2 still?
Nope, because I already did that back when I took out the 1/2, I multiplied that problem by 2.
That's right.
So yeah, you don't have to multiply it at the end. Now that's one leaf. If I wanted to find, because remember, if we looked at this one from 0 to 2 pi, it's actually 4 leaves. So if I wanted to find the area of the whole shape from 0 to 2 pi, I would just take that pi over 8 and multiply it by 4 and get pi over 2. So you can find the area of the whole thing now. It does not. Does that make sense?
Yeah.
Okay. All right. Last thing, arc length. So our arc length formula is going to be similar to what we did for the parametric equation. Just again with the thetas, it gets a little more complicated. Remember my dx d theta is that, my dy d theta is that. So when we're looking at my cosine theta squared, sine squared theta, that equation that we used before, we end up getting dr over d theta squared plus r squared. So, because remember, we're basically doing that Pythagorean identity or that theorem. So this is my original function, and then that would be the function that we're going to end up using. So when we look at it as continuous, so we have the dx d theta squared, dy d theta squared, and that simplifies down what we're doing with what we just did to r squared plus dr d theta squared. So you're still finding the derivative of it, you're plugging it in. The other one is just going to be that equation that they gave you squared. The one downside to this equation is sometimes these problems are not easy to integrate out. And they, of course, pick an example that's not easy to integrate out. But they want to look at the cardioid. So if we're looking at the cardioid, we have 1 plus sine theta. So we're going to plug that information in. So I have r squared plus drd theta squared. Remember when we did that originally, the drd theta is just cosine squared theta. And my r squared is 1 plus sine squared, or sine theta. You cannot just take the square root of those and get rid of those squares. It does not work that way. So we have to FOIL this out. So we get 1 plus 2 sine theta plus sine squared theta plus cosine squared theta. And when you have sine squared theta and cosine squared theta, that equals 1. So you're left with 2 plus 2 sine theta. So the only way to actually integrate this one is you actually have to rationalize the numerator. So you're multiplying by the square root of 2 minus 2 sine theta, and you're going to end up getting, you'll have something that you actually can do the integration of. It's a long and drawn out process, so we're not going to do it right now. But if you solve this out, or we could use a calculator to actually get the answer, it comes up with the cardioid. The length of the cardioid is 8. Don't worry, we'll actually do one that's a little easier to calculate out. So you can actually see one done. Where is it? There it is. All right. Let's actually do one out. I just got to find one that works easily. All right. Yeah, let's do. All right, let's do 40. Let's do that. So I want to find the exact length of this problem. So we have r equals 2 cosine theta. And my equation goes from 0 to pi. All right, so let's work our way through this one. So there's my function. So remember my arc length equation is a to b r squared plus drd theta squared d theta. So I've got my r, so I need to find my drd theta, which is just the derivative of that. So in this case, it's going to be negative 2 sine theta. So my arc length is going to go from 0 to pi. R is 2 cosine theta squared. and then plus -2 sine theta squared. So if we do this out, I have 4 cosine 2 theta plus sine squared theta. Everybody see where I got to that point?
Yep.
All right, so now cosine squared theta plus sine squared theta is what? That's your Pythagorean identity, so that equals 1. So I just get the square root of 4. So I'm doing the integral from 0 to pi of 2. So that's 2 theta from 0 to pi. So it ends up becoming, the answer is 2 pi. So that's the arc length. Questions on that one?
No.
Okay. All right. That's it.